final point I want to discuss what happens to large deviations where when you have distributions for which the decays at infinity slower than an exponential. So again, I remind you that we have a sample which is a sequence of IID random variables and IID random variables, and from some distribution Q of x. So, and we are interested in atypical events where, say, an this atypical event an of x, where the sample mean takes up a value which is different from the expected value under Q of x. Okay? So we have said that in the standard recipe for doing for discussing this case is to compute this function here, which is the logarithm of the expected value of under Q of e to the h times x. Now, this object here is the integral from minus infinity to infinity in dx of p of x e to the h times x. So this will be finite only if p of x goes to 0 faster than an exponential. Okay? Or as an exponential or faster than an exponential. Okay? Otherwise, this integral is not finite, and you cannot start. I mean, your starting point fails because you cannot compute this function phi of h. So what happens then? Okay. So how do we describe large deviations in this case? Notice that we are not only describing power law distributions where the first moment and the second moment may not exist. We are also discussing probability distributions such as, for example, e to the minus the square root of x, of the absolute value of x, where all the moments are finite. All the moments of this distribution are perfectly finite, but still you cannot compute large deviations with this recipe. Okay. So what happens? What happens then? Okay. So let me take a particular example where where say Q of x is something like I don't know, maybe a constant times 1 plus x. The gamma with some gamma which is larger than 3, so that the expected value and the mean, the expected value and the variance are finite. So we know that the central limit theorem holds, the law of large numbers holds, and then we want to compute the large deviation for this function, where let's say x is positive. Okay. Now, when I solve this problem, as soon as h is negative, then this integral converges, because q of x, all these random variables are positive, so the support of this distribution is also only on the positive side. So that this is just the logarithm of the integral from 0 to infinity dx of e to the minus h times x divided by 1 plus x to the gamma. So this is finite, okay? So this is finite for h, which is non-negative, okay? So then what we can do is to say, well, okay, I compute x bar, which is the derivative of this, and this is the and this will be defined for all h which are negative. Okay, so this h of x will be negative, so I can plot this function. It's a function of h. So of course, if h, so when h is equal to 0, we know that this function should approach to, so this is the function x bar of h. And so when this function is, when h is negative, then this function is smaller than this point, and this point corresponds to the typical behavior. Okay. So if I want to solve large deviation for deviation which are smaller than the expected value, than the typical value, then I can apply just the recipe I mean, I can just apply the usual Legendre transform. I can just Legendre transform this and compute this function h bar. I compute this h star, and everything works fine. Okay, and as a result of this, I can draw the curve of I of x for all the points which are less than the expected value of q of x. And what I will get is, well, the usual, say, curve, which essentially will go down, will be 0 here, and we know that it goes to 0 quadratically because of the central limit theorem. Okay, if I expand this function for a smaller value of x bar here, then I will get a quadratic function. Okay, very good. But what happens if I look at the deviation which are larger than x bar? What happens in this region? Okay, so clearly I cannot apply this argument here. So what I can do is to look at a particular set of events. Let me say, let me call this a tilde of n of x bar. And these events are such that, are all the samples, such that n minus 1 of the variables are typical in the sense that their average is essentially equal to x bar. So I can define these with epsilons, and but let me just define this in this way. So n minus 1 of the variables are typical in the sense that their average is equal to, sorry, the expected value of x. And one variable instead is very large. It's of order n times x bar minus expected value q of x. Say for some I star, okay? So you see that if I if I take the average, then the average, well, actually we should put plus expected value of q of x here. So this event is an event where this condition is satisfied, okay, but it's satisfied in this particular way in which n minus 1 of the variables are typical in the sense that their average takes is equal to the expected value, but one of the variables is very large, is of order n, okay. Now, of course, this event a tilde n of x is contained into a n of x. So the probability of a n of x will be less or equal than the probability of a tilde n of x. Okay? But what is this probability? Well, you can estimate this probability. So these variables are independent. So essentially, you can choose this I star in n ways. Then the variables are independent. So the probability that n minus 1 of them have an average which is equal to the expected value is 1 by the law of large numbers, asymptotically. And then you have just the probability of this very large value of xi bar, xi stars. So that one of the variables takes this very large value, okay? So, so you see from this that when you compute this limit, which is minus 1 over n minus the log, the limit as n goes to infinity of 1 over n times the log of the probability of a n of x. This must be less or equal sorry, this so the sorry, this is the other way around, okay? The probability of this must be larger or equal to the probability of this. So this I of x should be less or equal then the limit as n goes to infinity of the log say of minus 1 over n times the log of the probability q of n times a constant. Okay, let's call it k. Okay, and now you see that because this probability distribution decays slower than exponential, then this limit is actually equal to 0. Okay, so what this tells you is that this function I of x is going to be equal to 0 for all values of x which are larger than the x bar, that are larger than the expected value. So this is a very interesting phenomenon, because it tells you that in this case, when you have fat tail distributions, then in particular when you have this type of situation, where you have a thin tail on one side and fat tail on the other, what you have is a situation where your large deviation function is a discontinuity in the second derivative. So it's has normal behavior until the expected value, and then it is flat. So this function has a second discontinuity in the second derivative. And what happens in the solution is that these two regions are markedly different, in the sense that in this region here, as we said, a large deviation is realized by each of the random variable xi being drawn from a modified distribution, which is the original distribution times e to the h times x normalized. Okay, so the distribution p beta that we discussed. So all the variables are again independent and identically distributed. What changes in this region is just that the distribution changes. What happens here is that, all variables but one are essentially typical. They are distributed like this, but one of them is special, and it is very, very large. Okay, and so this is a phenomenon that you see it's like a symmetry breaking, because your variables that were a priori symmetric, in the sense that they were identical, a posteriori, when you see a large deviation, they are not identical, because one of them is much larger than the other. And which one of them? Well, any of them. So I star can be any of the random variables. So this is a situation where the symmetry, the permutation symmetry between these variables is broken spontaneously. So so there is no a priori reason for choosing one particular of these variables. So this connection between having a state function or a function which has a second order singularity in the second order derivative and having this phenomenon of spontaneous symmetry breaking is also what happens in physics, in statistical mechanics, when you study second order phase transition. So in physics, you define the order of phase transition by the order of the singularity of the thermodynamic potential. Indeed, we will see that the rate function is the entropy, so is a thermodynamic potential. And here you see precisely that we have a second order singularity, a singularity in the second order derivative of this potential, and this is accompanied by this feature by which a symmetry in your problem is spontaneously broken. Okay?